Record now. Okay, first of all, sorry for yesterday. The connection was not good and keep disconnecting, so this replacing yesterday's session. So today we will be going through the module 2, which is talking about structure analysis and limit state design of steel structure according to Australian Standard 400 4100. The topic we will be looking at today are the material and design requirement of steel structure, structure analysis and design, limit state design, which include two types, ultimate limit states, and serviceability limit state. And also we'll be looking at the loads and load combination on steel structures and how to estimate or calculate the load on structure members like beams and columns. So this is the main topics we will be going through today. At some points we'll go like not in depth, and some points will go in depth. So let's start with the material design requirement. So the steel products, as you know, it's mainly from iron and also can contain some other material to strengthen the steel, which is carbon or silicon or manganese. The important properties of steel are strength, ductility, impact resistance, and weldability. And as you know, the most important properties of steel is ductility and high strength. The main element in steel building are steel plates. You can find steel plates or standard section. So as you know, steel plates might have plates like that, or standard section like I-beam or channels, and also compound section, which can be some section welded together or bolted together. So for example, something like this. So these are the available sections type. Okay, other forms of structure elements can be found from these elements. General division is made between hot rolled and cold formed steel. So we have two types of steel section in the market. We have hot rolled steel, which is a little bit thicker, and we have cold formed, which is thinner. So maybe the cold formed are the most common one are Z section and C section. The most common hot rolled is I-beam or broad flange I-beam or UB section and so on. The main difference is this cold formed is thin. The hot rolled section are thicker. Okay. Our course will be focusing on the hot rolled section. So we'll be focusing mainly on the hot rolled section. Also, the Australian Standard 4100 is mainly for hot rolled steel. For cold formed steel, there is another standard which AS for 4600, which is giving the design criteria and design procedure of cold formed steel. For economic reason, the standard section is preferable because it is available and easy to get. Here there is some or a comparison between hot rolled and cold formed steel, and you can go through this one. The hot rolled steel are mainly made or be fabricated under high temperature, 1000 Celsius, can be shaped and formed easily, can be made in larger sizes because it is thick, so it has more stiffness compared to the cold formed steel, and cheaper than cold formed steel or cold rolled steel because it doesn't need advanced machine to roll the steel. When the steel cools off, it shrinks slightly. So this is one of the disadvantages of steel or hot rolled steel, because it is after the temperature cool down, it shrinks slightly. So this means that we have less control over the size and shape of the final product. The hot rolled steel also used in railroad tracks like I-beam, which where precise shapes and tolerance are not required. So one of the shapes of the rails tracks, something like this. So it is from hot rolled steel. The other type is the cold formed steel, which is essentially hot rolled steel with further processing in cold reduction mills. Material is cooled at room temperature, followed by annealing or timber rolling. So it's just because the steel is need to be melted to be formed. Then after it cool, it bent or taking the shape using the rolling machine. It has higher yield and higher tensile stresses compared to the more than the hot rolled steel. So this is one of the advantages. Fewer surface imperfection, closer dimension tolerance because you do it by machine, so it has better tolerance or better quality control. Superior surface finishes and straightness used in any project where tolerances and surface condition are major factor of the structure. And this is the shape of hot rolled steel, and this is the shape of cold formed steel. This like rod, sorry, parallel flange channel or channel BFC, and these are several shapes of the C sections from cold formed steel. So as you can see, here is the section is a bit thicker than here. Okay, this is a video to see the difference of processing of cold formed and hot rolled steel. The section of hot rolled steel and cold formed steel. Hot rolled steel, we have universal beam or I section, in abbreviation UB. Very efficient section for resisting bending moment about major axis. So this is our this axis. So this section is very strong to resist the moment in about X direction. We have also universal column or H section with the abbreviation UC, primarily to resist axial loads with larger radius of gyration about the minor axis to prevent buckling in plan. So it is almost the same, but it has maybe wider flange compared to the UB. So UC and UB, this is UC because it has the height of the cross section is very close or equal to the width. And we have channels used for beams or bracing or truss member or compound members, equal and unequal angle. So equal EA, unequal angle UA. So equal angle, so it is angle, the two legs LL, unequal angle with two legs L1 and L2. The unequal angle and unequal angles can be used for bracing member, truss member, and purlins. This is for the hot rolled section. For the cold formed section, we have circular, square, and rectangular hollow section. So this is a square hollow section. This is circular hollow section, and might be also rectangular, so rectangular hollow section. So very efficient compression members can be used as a compression member. used in wide range of application. As remember, roof trusses, lattice girders, building frames, purlin, sheets, and so on. Okay, so these are some examples of the cold format section. We have also some compound section, which is tracing a whole rolled section such as universal beam by welding on cover plates or other section, combining two separate rolled section together. And we have also built up section. The built up section similar to the one we ended the lecture last week with, built up girder or welded girder. Like we have plate acting as a web, welded to another plate acting as a flange, and welded to another plate acting as a bottom flange. So in here between the web and flange we have some welding here, and between the web and bottom flange is also welding here. So this is called built up. If the available section in the market is not sufficient, so we can use built up sections, which again weld plate together forming I or H or box member. Example, we have plate girders or built up girders, built up columns, box girder or columns. We can also have built up cold format section used in purlin, side, and sheeting rails. So this is a quick view about the available sections on the market. And here is some cross section that we was talking about. So this is the first one. Here is a plate element. Here is UB and here is UC. As you can see, the difference between UB and UC is the width of flange compared to the web. And also we have WB, which is welded beam. So the plates and 3 plates are welded together to create something, a beam or a section similar to UB. Here, welded column. The difference between, again, welded beam and welded column is the width of the flange. And also here we have taper flange beam. As you can see, we have a little bit inclination in the flange here. So if this T1, so we have here T2. Here also the parallel flange channel and equal angle, unequal angle, and we have here flat bar or flat plate and square bar. So all these are continuous. So it is like solid square section, solid sheet, and here also round bar, solid round bar. For some of the cold format section or structure hollow section are circular hollow section. So it is a square section but hollow. So this lighter. So square hollow section. Sorry, circular hollow section, rectangular hollow section, and square hollow section. Okay, here are some common section used for beams. Like again, UB, WB, and this is some compound sections. Okay, so these are some examples of the available section in the market. And now we jump to the physical properties of the steel. So the material properties of steel are measured by tensile Coulomb test. So this is the main test for steel. So the Coulomb is similar to a dog bone section, like that, cut from the steel. This can be an example. If it is sheet or something like this, another option is if it is a bar or something, so something like this. So we have just trying to have neck, and here is the width here, B1 more, greater than B2, just to force the failure or the rupture of the section to be in this area. And then this bone or this dog bone is under tension to see how much is a failure load. So using this test, we have typical stress strain curve for mild steel and low steel, because we have some or different type of steel. We have for mild steel and for low alloy steel. So if we look here, for example, let's look at the one to the right first, this one here. So this is the typical stress strain curve of steel. As you can see here, the strain on the horizontal axis and the stress on the vertical axis. So we have linear part up to here. The end of this linear part is sigma yield or the yield strength. Then we have an area of stable stress or constant stress. Then strain hardening start to happen in this area. So up to the peak. The peak is called ultimate stress or sigma U. This is the maximum stress can be obtained by steel. Then after that, we have the failure or necking of the steel. So that the strengths start to drop until failure or rupture at this point. Okay. And here, this point here is epsilon yield. Here also epsilon yield permanent, and here epsilon ultimate. Sorry, the other one here is epsilon ultimate. Okay, so this is a typical stress strain curve of steel. And here in this to the right, we have higher grades of steel, which have some carbon, so it is a little bit brittle, more brittle compared to mild steel because it has carbon inside. So as you can see here, for lower yield strength or lower strength, we have typical to the curve on the right. Then after that, when the strengths go higher, we can see that the yield point is not clear and the steel start to be more brittle. Okay, so this also some steels behave like that because of high carbon inside. So the high carbon make it more brittle compared to the mild steel. Okay, these are some explanation of terms of the curve. So we have elastic limits, which is greedy stress at sigma yield. We have elastic range, portion where Hooke law applied or applicable proportionally. Here, so in this area, only this area here. So if we take this out, so we have sigma yield, we have epsilon yield, and the inclination will be E. So this E1, so E equal to sigma yield over epsilon yield. So this only applicable at the elastic range. The elastic range where the stress remain constant for certain range of strains. Okay, the strain hardening range portion immediately after the elastic range starts. So from here. So this is the strain hardening area and so on. The yield stress F yield again is the stress because the most important is this 3 for the properties of steel. So ultimate strength F ultimate, the maximum stress of the tensile piece can sustain at the top of the curve here. So this is sigma ultimate. Sigma yield or F yield is the yield strength at the end point. For steel without a clearly defined yield points, a proof stress is used instead. The Young modulus or modulus of elasticity E, it is the slope of the initial linear portion of the stress strain curve, which is here. Also, for your information, E is a constant for steel, and it is around 200 to 210 gigapascal. So this is the value of E. Okay, so this is the value of E, because sometimes we need it. Okay, this video is showing a standard tensile test of steel. Okay, do you have any question, guys, up to now?
No, all good.
All good, thank you.
Thank you. Okay, so here's some example of the available steel or structural steel in the market. So again, the yield the yield strength or the yield stress F yield is the most important parameter in the design process because all the design is based on F yield, not F ultimate. So mostly F yield, not F ultimate, because if you design for F ultimate, this means that when the steel reaches this point, the building or the structure will start to fail. So we just try to avoid that and working on the yield strength. Here is some parameters or some values we need to keep in mind when we are working with the steel. So the Young's modulus E is again 200 gigapascal, equivalent to 200,000 MPa. The shear modulus G is 80,000 MPa. Coefficient of thermal expansion, 11.7 times 10 to the power 6. The Poisson ratio for steel is 0.25. The density of steel is 7,850 kilogram per cubic meter. Okay. And also here is some of the properties of steel at elevated temperature if required. So as you can see, what you can see when the temperature increase. When the temperature increase, the properties of steel decrease. So temperature increase means probabilities decline or decrease. Okay. So this is logic because when you elevate the temperature, the steel lose its strength. Okay. These are some specification and strengths of typical steel. Important consideration regarding the type and the grades for structure application. The steel should be weldable or has some weldability properties, able to be welded with ease without complicated procedure. Ductility. The whole concept of structural steel design is based on the ductile behavior of structure. So again, these two properties are very important in steel. Low cost to strength ratio. Availability of section and splits. Availability of mild steel grades are generally higher than higher strength steel because higher strength steel need to, more carbon. So the mild steel is more available and more cheaper than the high strength steel. Steel types and the grades refer to the standard 4100. Thinner plates generally have higher yield strengths. This is the table of steel strengths available on the Australian market, and we have some standard for the steel itself or the steel types itself. So for example, we have AS 1163 for hollow sections. We have this grades for hollow section. For hot rolled section, we have these two grades, or sorry, all these grades. Okay, so we have grade 450, 400, 350, and 300, 300 plus, and 250. So all these grades are available for the hot roll. Let's focus on this one. So for example, the grade 450, this means that the yield strength is 450, and in some cases, because when the thickness increase, they reduce the strength a little bit. So it is ranging between 400 to 450 based on the thickness. Grade 400, so again 400 yield, 350, the grade is 360, 300 is 320, 250 is 280. Okay, so this is the available steels in the market. And also, as you can see here, the tensile strength Fu, here is yield strength Fy. Fu should be greater than, by logic, should be greater than the F yield. So for 450 grade is 520, and 480, 450, 450, and 410. Okay, so this all properties are available in the Australian standard for this section available in the market. There are some other structural steel properties which might need to be considered when designing or when doing some research about steel. So, for example, residual stresses. We can go just briefly on this one. So, the residual stresses, the stresses that remain of an unloaded member after being formed into finish due to cooling or after hot rolled or welding. So after you apply temperature to the steel, there is some residual stresses will be remaining on the steel. Okay. So this residual stresses must be in equilibrium, and this will cause an effect on the structural behavior is limited. So if the residual stresses are in equilibrium, so the effect on the behavior of the structure will be limited. Okay, these residual stresses are important in compression member, where the region contain residual stress compression yield stress at less than B yield. So it is important in the compression member to keep the stresses less than the yield stress. Here is some example of the residual stresses. Okay, if we look at this one here, hot rolled I section. So we have some stresses like that on the member. So some stresses are compression and some stresses are tension. So this is the shape of the stresses on the hot rolled section. As you can see, it is very small at the edges and maximum at the middle. Here also on the web, very small at the middle, at the ends, almost zero, and maximum at the middle. Okay, so this is one of the things we have on the steel after, or the problems we have with hot rolled steel due to high temperature and cooling off. The other vulnerability or other disadvantage we have is the fatigue. Structure subjected to many cycles of fluctuating load, let's say more than 100,000. So this, you keep applying the load and releasing the load, applying the load, applying the load. So this is called, or this caused fatigue. So the fatigue is caused by applying many cycles of the loads. Failure occurs by the continued growth of cracks at the stresses below static yield stress. Fatigue is unlikely in normal civil engineering structure, but it mainly in the structure subjected to dynamic loads. So if the structure under dynamic loads, so it will be subjected to fatigue. Some exceptions are crane girders, railway bridges, offshore structure. So these are the structure we may need to consider the fatigue, because, for example, the railway bridge, the trains keep going and passing on the track, so this causes fatigue in the fatigue on the structure members or the rails. Also, we have brittle fracture. Steel become brittle when the temperature drops to below 100 Celsius. Fractures can occur at low stress below zero stress. So when the steel is at low temperature, so this might cause freezing of steel or at freezing degrees. So this causes the steel to be more brittle and subject to fracture. So this means the steel loses the ductility. Choosing the steel quality grade with adequate impact toughness. So we need to choose better or steel with advanced properties in this weathers. Also, one of the problems we have is the fire. So steel performs badly in fires because the strength decrease. At 550 Celsius, yield stress falls to approximately 0.7 of its value at normal temperature. So this means that the steel loses 30% of its strength at 550 degrees. So fire protection may be needed or can provide by encasing the member in concrete. For example, this is a cross section, so we can, if the column, for example, will be subjected to fire, so we can embed it in concrete. So this is, the green is concrete. Okay. Or cementitious fiber material. Also, intumescent paint can be used for exposed steel work. Also, some paints can be used to add fire protection to steel. If there is no option to add concrete, or there is like no funding or no, for economic issue, we cannot add concrete, so some paints can be added. Also, one of the problems is the corrosion. So as you know, steel is subject to corrosion in like wet or humid weather. So some protection may be added. So provide surface protection like metallic coating or venting. Some careful detailing can be used or followed to avoid upturned channel forming cavities to collect water. Okay, also for transition temperature, ductility of steel is normally tested at room temperature. So the ductility is at room temperature, not at low temperature or high temperature. Ductility diminish at lower temperature. So this what we was talking about, the brittle behavior. Okay, so this all was for the material properties and the material and properties of steel as a material and a section. The second part of our lecture is the structural analysis and the design. So for structural analysis and the design, we have conceptual design process. So the architects are usually responsible for problem formulation and conceptual design of the building. Some early considerations we should follow is to identify the purpose of structure, like building, factory, house, or hospital, and so on. Amount of space enclosed, so need to know what is the layout of the building and what is the space required based on the usage of the building. Assessment of the site, selection of the material, economic, strength, appearance, thermal, sound insulation, fire protection, and durability. So this all should be considered when choosing the material. The loading, what are the type of loading? Heavy loading or possibly cycling or earthquake, snows, or dynamic loading. So you need to know also what type of loads are subjected to the building or the element to select the material based on that. Local government regulations potentially affecting the design. And also we need to check if we have or we are in corrosive environment, for example, offshore building, offshore structure. So it is subjected or exposed to wind and water all the time. So this will be a corrosive environment. The second is engineering process or engineering design process, which is our rule. So designer core task is conceive the structure in accordance with the design brief and relevant standards and requirements, and other constraints like cost, site condition, time frame, availability of the material, construction technology, and client preferences, and ensuring that the structure will perform adequately during its design. So we have some phases of the design. We can go through this one. We have investigation phase, and again, then the conceptual design phase, and we have the preliminary design phase, which is our job, and the final design phase and documentation phase. So preparing the shop drawing to be ready for executions, and tendering phase and construction phase is the last step. And now let's go to the structural design principle. So our role is structural design. So what is the principle of structural design? The principle of structural design is the objective of the structural design. Firstly, what is the objective of the design? Is to define a structure that capable of remaining fit for the intended use throughout its design life without a need for costly maintenance. So I need to design a building that is durable and reliable with lower cost maintenance. Appropriate methods of analysis to predict the strength and surface load of the structure. The codes and standard are playing an important role, so we need to stipulate minimum structural performance level, strength, and serviceability that legally must be met. So for steel, we have AS 4100. For reinforced concrete and pre-stressed concrete, we have AS 3600. Most decisions are interrelated. This means that the design process is iterative, not from the first step. Okay. The structural design requirements are serviceability, strength, durability. So serviceability means that the structure will perform well under day-to-day surface, no excessive deflection or excessive cracking. For example, if you have a building, so we need to make sure that the deflection of this building or this roof or this beam is lower than some allowable limits. The strength means adequate strength to resist overloading or environmental extremes. So, for example, if we have building with some unexpected loads like intensive wind or high earthquakes, so the building still should resist these forces and stay without collapsing. Durability means the building don't deteriorate rapidly and could function with undue maintenance and repair over its design life. Robustness means the ability to resist unexpected and accidental loads and actions, such as blast or collisions. Some other criteria we need to keep in or we need to follow is the fatigue and fire resistance and vibration control in some structures. Non-structure criteria are the appearance and aesthetic of the building. Okay, for the structural modeling, we have real life structure, and we can have analytical model and physical model. Analytical model means idealized and simplified representation of the complex real world structure, retaining its essential aspects, which we are using in our design. This is a starting point of the development of any theoretical analysis or design. Thanks, Ilya. No worries. The physical model is small-scale prototype using the same material tested in the lab, useful to study complex phenomena and complex structure. So our focus will be on the analytical models. The structure analysis, which is needed to calculate the loads or the applied loads on our buildings. Again, we need to know what is the objective of the structure analysis. Sorry, what is the objective? The objective of the structure analysis is determining the internal forces and the moment, the design effect. So if the structure is determined, so we can use engineering statics. If it is indeterminate, so more advanced methods are needed. So in the complicated or indeterminate structure here, we can also use some software packages like MicroStrand, Space Gas, Multiframe, and Strand 7. So any of this software can be used for structure analysis. Do you have any idea about any of these software?
Yeah, some of them.
Have you used any of them in any other course?
Yeah, Strand 7 I have.
Okay, and others, have you used any other software? I mean, other guys.
Yep, I used Space Guest, but it's only for the basic term for the last year study.
Yeah, like getting the moment and shear and so on, like for structure course or something like that.
Yeah, yeah.
Yeah, because we might need to use one of the softwares in the portfolio, so that's why I'm asking. Maybe we can have a short session about that, or have a discussion about that later in the course.
Yeah. So do we need to use any softwares for any assignments?
Yeah. For the portfolio, we might need to use, because we'll have a frame structure that is not easy to solve manually, so we might need to use one of the software like Space Gas or Strand 7, either of them,
Oh, yeah.
to find the bending moment diagram and shear force diagram and so on.
Yep. Okay. No worries.
Space Gas is easy to get for students, so just need to maybe send them email or something, request access, and they will send you a link. And also, Space Gas is much easier compared to Strand 7. Okay, we might talk about this later, maybe next week lecture or week 4, because we will need it only on the portfolio. So assessment 3. Okay, thank you guys. Okay, so these are the software that are common in the Australian market, so they use it in the consultation company and so on for design. Okay, the input required for software are the geometry, member, and connection properties and boundary condition. Like for example, if we have a frame, so you need to know what are the supports, what are the dimension, like height of the frame, width of the beam, and also you need to know what is the material, like for example steel, what is the cross section, for example it is I-beam or U-beam or UC, and so on. Okay, so this is geometry and material properties and so on. And then you need to know the design action like dead load, live load, wind load applied to the structure. The output of the software is a design action like moment, normal force, and shear, and also the deformation or the deflection, mainly the deflections. Okay. So the method of structure analysis range from simple to complex depending on the structure form. So you might have elastic analysis or plastic analysis. The elastic analysis means you are in the elastic zone of the material. Do you remember the steel, like stress strain curve of steel? So we have this zone. So here sigma yield, here epsilon yield. So this is E. So this is a linear zone. So which means the elastic zone. In the plastic analysis, we after the part after the elastic zone is called the plastic zone. So in the plastic zone, we might have plastic hinge are assumed to sorry guys. Okay, so again we have the input of the software and output of the software. So the input of the software is the frame geometry, member and connection properties, boundary conditions, and also material properties. Also what we need is the design actions like dead load, live load, and wind load applied to the structure. The output will be the design action effect like moment, shear, and normal or axial forces. All these are output of the software, and also the deformation, which is mainly deflections. Okay, the method of structure analysis ranges between simple and complex, depending on the structure form. We might have elastic analysis. Again, this is in the elastic zone of the material. Okay, where if we have this sigma yield and this epsilon yield, where the relation between sigma and epsilon is linear. Okay, this is simple because the material is the behavior of the material is proportional between the stress and strain. The second type of analysis we might have is the plastic analysis, which is a little bit more complicated. This is in the plastic zone here, after the elastic zone. In the plastic analysis, we might have plastic hinges are assumed to occur at the critical local region where collapse is imminent. For example, yield line analysis for the two-way slab. This will maximize the structural capacity, more economical, less conservative. So the plastic analysis will be more economical because you try to utilize like full strength of the material. So this is the main idea, the full strength. Availability, the drawbacks of this method is the availability of software. Not many softwares can apply the plastic analysis, and also takes time and labor intensive. The third is advanced analysis, which more complicated compared to the plastic analysis. The methods of analysis we will adapt, or you can adapt in your design, depending on the degree of accuracy required, the time required to assemble data for rigorous analysis, and simple methods are usually employed in the preliminary design. So In the preliminary design, you can use the simplest method. And also, if the degree of accuracy is not high, you can use the elastic analysis. So mostly we use elastic analysis based on the requirements we have in our projects. So let's start with some idea about the elastic analysis. The elastic analysis, which is in clause 4.4 in the Australian Standard 4100. The linear analysis or the linear elastic analysis, this analysis has been used as the basis of all structural design due considerably simpler analysis. Individual members are assumed to remain elastic under the action of design loads for all limit states. So this means that after applying the load, the element or the structure stay elastic. The Australian standard requires second order analysis to be considered in some cases. So the second order effects are included in the elastic analysis. So the design loads acting on structure member and their deformed configuration shall be considered through either two methods. First order elastic analysis with moment amplification in clause 4.4.2. This method will need the provided moment amplification factor delta B or delta S less than 1.4. This method is preferable when the manual analysis is carried out. Another method is second order elastic analysis in Appendix D of the standard. The second order effects are attributed to geometry change during the analysis. Deformation of structure and design action effect are coupled. So this method has different procedure compared to the first one. The first one is just if you have the applied moment is M. So to account for the second order effect, you need to multiply it by a factor or amplification factor called delta B or delta S. So this is the idea of the first order analysis. The second order elastic analysis, like take into consideration the geometry change during the analysis. So this is more advanced or more complicated. Second order effects can sometimes be small enough to be neglected. In some cases, you can neglect the second order effect based on the standard regulations, except in special structures such as unbraced multi-story frames. Some computer programs, such as Space Gas, can carry out first order and second order analysis. So in Space Gas, there is option for first order or second order analysis. Okay, let's again, so this is some forms of constructions assumed in or for structure analysis. The distribution of design action effect throughout members and connection of a structure takes one or combination of the following. So the connection can be rigid or semi-rigid or simple connection. So the rigid connection assumed to have sufficient rigidity to hold original angle between the members unchanged. So for example, if we have a frame, so this frame has 90 degree between beam and column. So after applying the load, this connection still same, even it has some rotation, but the angle is still 90 degree. So if this happens, this means the connection is rigid. Semi-rigid connections may not have sufficient rigidity to hold the original angle between the members, but shall be assumed to have the capacity to furnish a dependable and known degree of friction restraint. These connections are more difficult to analyze, usually avoided in practice. Actually, the semi-rigid is something between the rigid and simple. So let's look at the simple. The simple connection are at the end of the member shall be assumed not to develop bending moments in simple construction. So for example, if you have a connection here, This is not a frame, so this is our beam and this is our column. So the connection between both of them is different. So this one acts separately, and this means that as a structure, like structure modeling, so this is the connection, simple or bin connection. But here for the rigid, this is the connection. So if the connection with no bin, so this is called rigid connection. Okay, so the rigid connection, the two members are connected together and share the stiffness, and the angle remains same after deformation. But for the simple connection, each member can rotate separately, and the structure representation of it is hinged like that. The semi-rigid is something between simple and rigid. So it doesn't hold it 100% or doesn't also allow each member to behave separately 100%. Okay, the design of connection shall be consistent with the form of construction. So if you like assumed the connection between this rafter and this column is rigid, so the design or the connection should be rigid like that. If you assumed the connection between these two columns and rafter are bin or simple, so the structure in real life should be considering this. Okay. Do you have any question, guys, regarding that?
No, sir.
Thank you.
All good, thanks.
So the assumption, we have some assumption in the analysis. So we have analysis of regularly shaped members, substructure isolation. So in some cases we can subdivide if the structure is like repeated, so we can subdivide it to substructures. Structure shall be analyzed in its entirety, except as follows. So if we have regular building structure, may be analyzed as series of parallel 2D substructure. Generally, analysis being carried out in each of two directions at right angle, except when there is significant load redistribution between substructure. So if you have a structure like that, the load will be redistributed between substructure. So you have to analyze the building as a series of parallel 2D substructure. Okay. Like for example, we have this complex building, so you can assume that you have two directions of the building. This is one direction, like that, and this is another direction. So you can assume that the building has two faces, and this is 3D. You convert this into 2D members or 2D frames. Okay, this is just some simplification to simplify the analysis. Okay, so these are some requirement of the or some like regulation of the standard. You can have a look on it. Okay, and now let's jump on this point. So the first and or second order analysis. So when to do first order analysis and when to do second order analysis. Okay, so the first order analysis is again simple elastic analysis. The computational process ends with the determination of axial and shear and bending moments. Also, the displacements of nodes are determined in the final step of the analysis, but no feedback is included on the effect of the changed geometry. So the elastic analysis will give us again normal force, moment, and shear forces, and also will give us deformation delta. So these are the main things we will get from the first order analysis. The Australian standard design actions due to simple displacement of the frame and deformation of the member action must be determined by a second order analysis. So the second order analysis sometimes is required by the Australian standard in some cases, such as the braced frame, where sway deformation are often too small to be considered, and also for unbraced sway frames rely on the rigidity of the connection. So in this case, sway deformation cannot be neglected. So when the sway cannot be neglected, the structural analysis or the second order analysis is a must. Okay, what is a sway and what is caused by? Sway is the lateral movement. So for example, if we have a frame like that, if this frame is subjected to horizontal force, so the frame will move like that. So the new position of the frame, the difference between the old position to the new position is called delta or sway. So this is the sway. Lateral or asymmetrical forces will cause sway. So the sway is caused by lateral force like that or asymmetrical vertical force. The sway is most oftenly by inadequate stability under significant axial force in the column. So also in some cases where the column is not stable, so it will be under sway as well. Okay, the second order analysis may be not required in some cases, such as flexure member with negligible axial forces, tension member, and also triangulated frame in which the member forces are predominantly axial and no transverse forces are applied between nodes and compression codes. The second order effects, considering a single story rigid frame similar to here. So this is a single story frame. So the first step, you need to apply or perform a first order analysis to get delta and M1. So if we look at this frame, so this frame is subjected to some lateral forces, V, and also some unequal vertical force. So under these forces, what will happen to this frame? This frame will be under sway and also deformation. So let's look at this one, for example. So let's say this is our deformation. So between the initial position to the last position, this is called delta or the sway. Okay. So to take this second order analysis, second order effect of sway, the standard give us an amplification factor. So let's see here if this our bending moment diagram on the structure. So as you can see, the solid one is the actual moment and the dotted one is the amplified moment. So the dotted one is amplified moment due to the second order effect. So the amplified moment, let's say the dotted one, let's give it M amplified. So M amplified will be equal to M multiplied by the factor, as we mentioned earlier, delta S for example. Okay, so this is the main idea about the second order effect in the analysis. So the first of all, you need to do the first order analysis to get the moment and the deflection. When both columns are deformed, the forces B1 and B2 will displace the nodes. Displacement and moment increases to delta 2 and M2 due to second order effects. The interaction between the axial and member curvature from flexure and sway deflections. So this is generally the idea is we are amplifying or increasing the applied moment due to second order effects. The second order effects, which mainly comes from sway. Okay, so this is the idea. And here is how to calculate the second order effects. You can use computer software when performing a rational second order elastic analysis. Design action effects M, V, and N are obtained directly. So using software, it will be directly including the second order effects. All the displacement are tracked during the process of evaluating the design action until all displacement converge. So also the deflection or the deformation through the process is tracked. This means that at each level of analysis, the deflection are calculated. If the conversion of software not achieved, this means the structure is unstable and you need to like remodel or reanalyze the structure. No further amplification factor is needed in this case. But if we are looking at the manual procedure using the moment amplification method, so the steps are elastic analysis, elastic first order analysis, then calculate the moment amplification factor, praised delta B or sway delta S, then check the moment amplification factor less than 1.4. So the maximum of amplification factor in the Australian standard is 1.4. So it cannot be more than 1.4. Then after evaluating the design, the final or the moment including the second order effect M star will be equal to the applied the actual moment multiplied by the amplification factor. Okay, so this is the steps. We have 4 steps to find the moments after the second order effects. We have some notes. Calculation of the amplification factor is limited to members in rectangular frames. So this method is only in rectangular frames. If delta more than 1.4, so the frame need to be redesigned because this means that the sway effect on this member is too high. Okay, so this means that you need to redesign or use a different method. Okay, let's now look at how to calculate the factors or amplification factor delta B for braced frame. So we have one method for braced frame and 2 methods for unbraced frame. Okay, we will have a look on one here and one here only. So for braced frame, delta B, columns and beams are braced. So there is no sway under loads. Okay, so this method only for no sway frames. So the first step is to determine the elastic flexure buckling load in OMB. These formulas are in the Australian standard. So in OMB for each braced member. So for each column, you need to find this one, which is the Euler load or NOMB. So NOMB will be pi squared EI over KE times L all squared. Then we need to calculate the factor of unequal end moments, Cm. So Cm equal to 0.6 minus 0.4 beta m and should be less than or equal to 1. So we have NOMB, then Cm, then calculate the moment amplification factor for unbraced frame, then we can find delta B. So delta B is equal to Cm over 1 minus N star over NOMB should be more than or equal to 1. Should be more than 1 because it is amplification factor. So the amplification means we increasing the forces, so the amplification factor should be more than 1. Okay, then after you calculate this delta B, if it is less than 1.4, it's okay. Else frame is very sensitive to B delta effect, then second order analysis, or you need to change the frame stiffness or increase the frame stiffness, maybe use a bigger section or so on. So we can use a bigger sections for column. Okay, then the final step E, to multiply the bending moment of the first order analysis by delta B to obtain the second order moment. So M star will be M from first order analysis multiplied by delta B less than or equal to 1.4. Okay, so this method is for the braced frame, and now we will later know how to calculate Cm. Okay, for unbraced frame or sway frame, we have two methods, sorry. We will focus on method 2. So for delta S, unbraced or sway frame, method 2, we can calculate from the elastic analysis load factor method, especially when first order deflection are unknown. Okay, so this method is preferable when the first order deflections are unknown. So in this case, delta S will be equal to 1 over 1 minus 1 over lambda ms, or equal to 1 over 1 minus 1 over lambda c. So we have two factors we need to know, lambda c or lambda ms. Lambda ms is the elastic buckling load factor for story under each under consideration. So for example, if we have like multiple story frame and this frame is subjected to sway, so this frame will sway, for example, like that. So this is the new, so this is our sway. So depend on which story you are calculating or designing. So we will have, for example, if we are in this story, so lambda ms will be equal to summation NOMS over L divided by summation N star over L. So if you have like column 1, 2, 3, so you need to find NOMS 1, 2, 3 divided by L1, L2, L3. So this is the numerator. The denominator is, we have each column, you have N star, N1 over L1, N2 star over L2, plus N3 star over L3. Okay, and NOMB again is similar to before, is the Euler load, similar to before. Okay, and what is lambda C? So L is the member length, N star is the applied axial force, Lambda C is the elastic buckling load factor determined from the rational buckling analysis of the entire frame, equal to the lowest of all the lambda ms values of the multi-story rectangular sway frame. So if you need to use this one, lambda C, so you need to do a rational buckling analysis. So the other option, or what we would be focusing on, is this term is delta S equal to 1 over 1 minus 1 over lambda ms, because we can easily find, or we can find lambda ms, so this will be our option. Okay, then after we get lambda m, sorry, delta m or delta s, okay, so the final moment will be by multiplying the bending moment from the first order analysis by lambda s to obtain the design bending moment. Okay, here is some notes. Delta B, if delta B more than delta S, then delta M equal to delta B. So here we have one of the notes you need to know is we have to calculate lambda B and lambda S for the sway member. For sway member, you need to find lambda B and lambda S. So if lambda B more than lambda S, then lambda M will be equal to lambda B. If lambda B is the greater, so take lambda B. If lambda B less than lambda S, then take lambda S. So this means that for sway member, we have to calculate lambda B and lambda S and select the greater of them. Okay, then the greater will be our lambda M. So lambda M is the greater of lambda B and lambda S. Okay, then the modified or the amplified moment will be M times lambda. Okay, what else you need to know to proceed to find this? Some information required. What is KE? NOMB again equal to pi squared EI over KE L all squared. So what is KE? KE is the effective length factor or the buckling length factor. So I think you might have seen this before. For braced member, we have three cases because the column can be fixed end or bend end. So we can have fixed, if fixed, KA 0.7. If bend, we have 0.1. If one fixed, one hinge, so we have 0.85. So this for braced frame. For unbraced or sway members, we have other supports because if it is fixed, this means the frame is braced. So to be sway, this means that the top support or the top end should be allowed to move or to translate. So we have other types of supports here, like rotation fixed but translation free. So this support is allowing rotation, preventing rotation but allowing translation. If it like this, so this means rotation free and translation free. So this means this point is a free point. Okay. So if we look at this one, if the bottom end is fixed and top end is rotation fixed, translation free, so take K as 1.2. And if it is hinge and top end is rotation fixed, translation free, take it as 2.2. If fixed at the bottom, free at the top, also 2.2. Okay, so this is the This is the KE factor we have in our in steel structure or in our structure design. So finally, again, KE will be one of the 6 cases. Okay. And the buckling length of the column LE equal to KE times L. Okay, another method is used to find KE, the member effective length factor for rectangular frame. And this method is this is called idealized or theoretical method, because in this case we assume that we have fixed or bin supports or bin ends, but actually in real life we don't have ideal fixed or ideal bin supports. We have something in the middle between them. So to calculate that, the standard give us these 2 figures or 2 charts, sorry. Chart number A for braced frame, chart number B for sway or unbraced frame. If you look at these 2 charts, you will see that on the vertical axis we have lambda gamma 1, and on the bottom, on the horizontal axis, we have gamma 2. Okay, and then each chart is representing one value of K. For the other one, also lambda 1 and lambda 2, and we have Ke. So to use these 2 charts, we need to find gamma 1 and gamma 2, and using the chart, we can find Ke. So this Ke will be more accurate value for the buckling length. So how to find gamma 1 and gamma 2? Gamma 1 and gamma 2 are the stiffness ratios at top and bottom end of the column. Okay, so again, if we have column, like for example, multi-story frame, and we have this column, so this column has a top end and a bottom end. So to know what is the support here, like fixed or hinge or whatever, so you need to have a comparison between the beam and the column at the top and beam and the column at the bottom. This is what we are doing. So gamma 1 and gamma 2 will be the stiffness ratio of the beam and column at top end and bottom end of the column. Okay, so what is gamma? Gamma equal to this formula. So gamma equal to summation I over L for the column over summation beta E I over L for the beam. Are you still watching, seeing my screen?
Yes.
Yeah.
Okay, because we just received another error. So I think it will, yep, crash again. Sorry, guys. Can we have a rest for maybe 2 minutes until I fix this one?
Yep, sounds good.
No, thank you.
Yeah, good, thanks.
Okay, guys, sorry, something need to repeat this part again. The Adobe crashed again. So again, we can have another method to find the buckling factor, Ke, the exact one. So these 2 graphs, these 2 charts are given by Stalin standard to find the K effective factor for braced frames and K effective factor for sway frames. Both charts are a relation between gamma 1 and gamma 2, and to find the value of the factor K effect. So each plot is representing one value of K effective. Here again, same, gamma 1 and gamma 2. And each plot is a value of K effective K. Okay, so if we know to use chart, you need to find gamma 1, gamma 2 to get the value of K effective K. Okay, so how to find gamma 1 and gamma 2, and what is gamma 1, gamma 2? Gamma 1 and gamma 2 are stiffness ratio of the beam and columns, or beams and columns at top and bottom end of the column. So stiffness ratio is a compression of a compression member with a rectangular loading and negligible axial forces in beam is equal to this formula, gamma equal to summation I over L for columns over summation beta effective for IL for beams, where I and L, I is the inertia of the beam and column cross section, L is the lengths of the sections. Okay, so the formula is same for gamma 1 and gamma 2, but just gamma 1 and gamma 2 top and bottom end. So where gamma I over L for column is the summation of stiffnesses in the plane of the bending of all compression member rigidly connected at the member and end and under consideration. Sorry, end under consideration. So for example, if we are, again, we have this column, for example. So we have some columns and beam, and we are looking at designing this column. So we have two ends, top end and bottom end. So for top end, we have B1, C1. So this is our connection here. So we have B1 and C1. So at the top end, we have only one column and one beam. For the bottom end, we have B1, or sorry, B2, and we have C1 and C2. So we have C1, C2. So here, gamma 2, for example, will be equal to I1 over L1 plus I2 over L2 divided by I beam over L beam multiplied by beta E. Okay, so this is the idea. After you calculate gamma bottom and gamma top, so you can get into the chart and find the value of Ke. So before that, let's first know how much beta E. Beta E is calculated using this table 4.6.3.4. So beta depending on the fixity condition at the far end of the beam. So the worst case or the conservative case, you can assume beta effective as 1. Okay, so this is the worst case if you don't know how to use the table and so on. So for example here, if the far end of the beam is bent, so beta effective is 1.5 in braced frame and 0.5 in unbraced frame. What does this means fixity at the far end of the beam? Let's look at B1 here. So B1 is a beam, so we have another end of the beam at this side, for example. Right? So this is what does mean fixity at far end of beam. So if this end is bent, so you take it as 1.5 in braced, 1.5 in unbraced. If it is rigidly connected, similar to the case we have now, so how much in braced and unbraced, it is 1. So in frames, usually beta effective will be 1. If the other support is fixed, or the other end of the beam is fixed, you can take it as 2 in braced and 0.67 in unbraced. Okay. So for example, after we get gamma 1 and gamma 2, if we have a braced frame, for example, let's say gamma 1 was 1.5. And let's say gamma 1 was 1.5 as well. So they are intersecting here. So what is the value of KE? It is between 0.8 and 0.85. So we might take it as 0.825, for example. So this is an example. If we got gamma 1, gamma 2, then go to the chart to find K effective as 0.825. And similarly here, so if we are in a sway frame, if it is 1.5 gamma 2 and 1.5 gamma 1, so they are intersecting here between 1.5 and 1.4. So K effective equal to, for example, 1.46. Okay, so this is how to use the charts for gamma 1 and gamma 2. The other parameter we need to know was CM. If we go back here, so we need to find CM. So we finalized in OMB after we get KE. Now we need to find how we can calculate CM. CM again is the moment amplification factor for the, CM is the factor of unequal end moments. So how to calculate CM again? So here is CM. CM is using this formula. CM equal to 0.6 minus 0.4 beta M less than or equal to 1. Again, the worst case you can assume CM as 1. So CM, highest moment amplification factor, occurs when the bending moment is uniform along the member. So in this case, CM equal to 1. So for example, if we have a member and the moment all the member is same value, for example, 40 kilonewton meter, so CM for this case is 1. Okay, so for the normal or general cases, CM is using this formula for braced frame, where beta M is the ratio between M1 and M2. M1 and M2 are the two end moments. So for example, if we have our member like that, so we have M1 in one end and M2 in one end. So this M1 and M2. So we have several cases of that because the moment can be in this direction or in this direction. So it depends on how is the direction of the two moments. But generally, BM is the ratio of a smaller to larger bending moment. So M1 is the smaller bending moment, M2 is the larger bending moment. So for example, if we have 10 and 5, which one is M1 and which one is M2? So the top one will be M2, the bottom one will be M1. And the value, the beta M, will be 5/10 equal to 0.5. Okay, but another thing we need to consider is the direction of the two moments. So when the member is bent in a single curvature, take beta M as negative value. When the member is bent in reverse double curvature, so beta M should be positive. What is the difference? So if we have these two, so we might have this case or this case. In this case, to the left, the moments will cause one or single curvature because they are both bending in this direction. So this would be our curvature. This is called single curvature. But if the two moments like that, so this side will go up, this side will go up, so it has double curvature. So if we have single curvature, take beta m as, sorry, if we have single curvature, beta m as negative. So negative value. If we have double curvature, so take beta m as positive value. Okay. Is there any problem with that? And here, for example, if we have uniform moment distribution, like for example, if we have same moment, like 5 kilonewton meter here, 5 kilonewton meter here, this moment is single curvature, so beta m will be -1. Another case here, if we have two same moment, but opposite direction like that. So same value, but they causing double curvature. Like for example, again 5 and 5. So beta m will be 1. This is okay, but positive because we have double curvature. Okay. And this table gives some idea about how is beta m and how much is cm. So if we go back here, after we got beta m, if beta m is known, so no problem with cm. So beta m will give us easily cm. Okay, there are some limitation of the moment amplification factor. You can have a look on them, but not the main thing we need to look at now. Okay, so we can have a look on all of that. This all in the standard. And do you have any question for what we have done up to now? Do you have any question, guys?
No, sir.
Okay, thank you. So now let's go to the limit state designs in AS 4100. So limit state designs of for steel structures are the state of loaded structure on the verge of becoming unfit for use. So the limit state means the peak loading or the extreme case of the structure. After this case or after this situation, the building or the structure will start to collapse or fail. The limit states occur due to failure of one or more members, overturning instability, excessive deformation, or structure ceasing to fulfill the intended purpose. Nearly all modern codes are written in limit state design. All the codes like Australian Standard, American Standard, European Standard. A basic framework within which the structural performance can be assessed against the various limiting conditions, beyond which the structure would become less than completely fit for the intended use. Recognize the inherent variabilities of load, materials, construction practices, and approximation made in design. Also involves the use of probability, because this case is based on, or this limit state design method based on that, assuming the case when the building will collapse, and then we design for this condition. So it has some probability of failure, allowing for consistent factor of safety. So we have also factor of safety and economic use of the material. Performance of structure can be assessed against various limit conditions or limit states. These are the available limit states in the standard. So we have strength limit states, So resistance against yielding, fracture, or collapse under predominantly static actions. Also, we have stability, resistance against overturning. For some cases in very tall and thin buildings, so overturning is main issue. So need to consider stability. Also serviceability, which is the limit of satisfactory surface performance, including deflection, sway, vibration, and so on. In our course, we are mainly looking at the strengths and serviceability. Okay, so this is the main limit state condition. Other limit state like fatigue, fire, earthquakes, brittle failure, brittle fracture, and durability. Okay, so the limit state design for strengths is in clause 3.4 AS 400 4100. The limit state for design for strengths, the structure including all the member should have design capacities more than the design action effect. Okay, so this means that if we have moment, applied moment should be less than the moment capacity of the member. So this is the main idea of the design. The capacity of the member is more than the applied load, or the applied load less than the capacity. Basic strength design criterion, the probability of failure in surface is near zero. So there is no option to fail under the actual applied load. In Australian standard 1170.0, there is 5 percentile values in the probability distribution curve. So 5% of failure, but not in the surface loads. In engineering design, failure probability acceptable to the public is 1 in 100,000 per year per structure. To verify the limit state capacity of a structure, you need to use the standard, determine the most adverse combination of actions that occur throughout the design life, determine the resistance, the design capacity of the structure. This is the general rule of the strength limit state. The design action effect is less than the design capacity or the resistance of the structure. So ED, the applied load or applied case, less than phi R. Phi R is the capacity. Okay, so this is the rule of the strength limit states. In table 3.4, the Australian standard give us the values of phi. Phi is actually a reduction factor of strength. This is like a safety factor. So because if the capacity is 100, so we assume it is 80 or something, or 90, and so on, or just a reduced value to have like a safety margin. So the standard give us the factor phi based on the applied action or straining action. Like for example, for bending, it is phi equal to 0.9. For axial compression, it is also 0.9. For axial tension, 0.9. For combined action, 0.9. In some cases, 0.8, like in bolted connection, it is 0.8. So generally for our design, phi equal to 0.9. This for the member. Under tension, under compression, under bending moment. And this chart is showing this is a 5 percentile of failure that can be happen using the ultimate limit state. The capacity factor phi is accounting for variability in strengths and effects of steel elements and connection. So again, phi is a safety factor. to allow for the defects and steel element and connection. Steel elements and connection. The other limit states we have is the surfaceability limit states 3.5 AS for T100. This is the location in the standard. So the surfaceability means the fitness of structure to serve the design purpose with limited deformation. Some of the surfaceability limit state includes deflection, sway, and slopes, vibration affecting human comfort and mechanical plant performance, loss of material due to corrosion or abrasion, blood slip limit states. But mainly we are looking at the deflection in this case, in this limit state. Vertical deflection limit states and serviceability requirements, Appendix B. So the standard also give us some allowed deflection or allowable deflection. So the idea here in the serviceability is that the deflection you got should be less than or equal to the allowable limit states or the allowable limits by the standard. So in table B1, some suggested limit for vertical deflection of beams. So if we have beams supporting masonry partitions, the limitation is delta L, delta by L should be less than 1/500. For all other beam, the total deflection should be delta over L should be less than or equal to 1/25. This means that delta should be less than span over 250. For example, if you have a simple beam or a beam and you got the length of this beam is 10 meters. You got the deflection from your calculation as like 50 millimeter. So delta is 50 millimeter. What is the allowable limit? The allowable limit is 10,000 over 250. So this gives you only 40 millimeter. So this means that the deflection 50 more than the allowable limit. This means that this beam is unsafe. So you need to recalculate or use a bigger section to reduce the deflection. So this is the idea about the like limit states, serviceability limit states, and so on. Okay, there is also some horizontal deflection limit state for some elements like the clad in metal sheeting, H over 150, masonry walls, H over 240. And here is some limit states, design limit states for stability. You can also have a look on that because it is not our focus on this course, so you can have a quick read on it. So again, this atoll structure, and we have applied subjected to some winds. So this building is subjected to overturning. So we need to make sure that the overturning forces is less than or equal to the stabilizing force or resisting force. To make sure that this structure is safe. Okay, so this are some stability also limit states. Okay, and the Australian standard 1170 provides some modified design loads. Like we have 3 of them: 1170.0, 1170.1, 1170.2, 1170.2 for the wind load, 1170.1 for the dead load and live load, 1170.0 for the load combination, and some other limitations. So these are 1170 codes. or standard. Give a reasonable upper limit on the load effects in practice, large enough to ensure the probability of overloading, small enough to allow for economic constructions, doesn't account for extreme incidents. Design load generally act in combination with each other. These combinations are given by 1170.0. Load factor, gamma, considers uncertainties in magnitude, distribution, and duration of the loads. So all these loads will be calculated using the 1170.0 because the steel standard is only for the design and properties of steel. So the loads will be obtained or calculated based on the 1170 standard. Okay, now we go to the loading and load combination. So as you know, we have several types of load. We have permanent action or dead load, DL, also can be G. So the dead load means that the load that doesn't move on the structure mainly comes from shelf weight on weight of the structure, slabs, beams, columns, and so on. Permanently fixed non-structural elements, partitions, fixed mechanical, air conditioning, and other plant. These are some typical unit weights of the material given in AS 1170.1. So, for example, for brick masonry, we have the unit weight as 1.9, and if it is for engineering structure type, if it is calcium silicate, so 1.8. Also for example, the roofing or corrugated shields, if the thickness is 1 millimeter, so the unit weight is 0.12 kilonewton per square meter. For example, the concrete reinforced with bluestone aggregate, so 2.24 kilonewton per cubic meter, and so on. So this table gives us some idea about the dead loads. Also, we have imposed action or life loads, again AS 1170.1, based on building use or structure use. So the life load is based on the structure used, arises from the intended function of the building, including people, traffic, and so on. And it can take the symbol LL or P. Highly time dependent and randomly distributed in space. Okay, and also we don't consider the considered load in this course, so we are mainly using the UDL or uniform loads. So, for example, if the building is for offices general use, so the live load is 3 kilonewton per square meter. For public assembly areas, can be 4 kilonewton per square meter. For roofs, in the standard, it is 0.12 plus 1.8 over A and minimum 0.25 kBA. So this is for roofs. The life load will be 0.12 plus 1.8 over A and should be not less than or greater than or equal to 0.25 kilonewton per square meter. What is A? A is the supported area by the element. Okay, we will know that later. Okay, and here it is from the standard. So this is for roofs, other roofs. So this is our formula here. Okay, so if you calculate 1.8 over A plus 12, if it is less than 0.25, This means you cannot take it, for example, 0.2. So it can't be 0.2, and the live load will be 0.25 kPa minimum. Okay, so this is what is meant by this formula, not less than 0.25. The wind action or the wind loads, again from AS 1170.2, estimation of wind load is complex due to large variation and influenced by several factors, including gusset speed in the region, the building height, terrain category, topography, availability of shielding. All these are factors affecting the wind speed and wind forces. The wind speeds varies with the geographical region, local terrain, and height. Increases with height above the ground. So if you have higher buildings, so the wind is higher, wind speed is higher. The wind pressure is proportional to the square of the wind speed. So the wind pressure is proportionally with the wind speed. So the pressure is proportional with the square of the wind speed. Okay, as you can see here, this is the variation of the wind loads and the pressure with the building height. So when the height increase, as you can see, the wind pressure increase. Pressure increase with height. Wind are stronger in more exposed location, like hilltops, foreshores, and flat treeless plains, than sheltered inner city location. So because open or exposed areas, so the wind pressure and wind speed are higher. Tall buildings are and structure in exposed location must be designed for higher wind gussets than low structure in and those in sheltered location. Estimation of wind loading is laborious and it is treated separately in 1170.2. This unit focuses on the procedure of estimating wind on rectangular building only. So next lecture we will be focusing on how to estimate the wind loads. Other lateral forces we might have is earthquakes, which is covered by AS 1170.4, but this is not our focus in this course, and also in Australia it is not common to design for earthquakes. But generally earthquakes arises from the structure response to base foundation movement, and it's called inertia forces. This inertia forces causing distribution of the structure mass and stiffness is not synchronized with the base movement. Okay, so you can have a look on this part. Other horizontal force we might have is the notional horizontal force. The notional horizontal forces equal to 0.2% of the design vertical forces for each floor level should be considered in multi-story building. And this should be considered in conjunction with vertical loads. Rationally, allow for minimum horizontal action arising from out of plumb tolerance limits 1/500 for electric currents. Okay, this also can have a read on this one, so not much required in this course. And now come to the next important thing, which is the load combination for strength design. As you know, we have like up to now 3 types of load: dead load, live load, and wind load. So these loads can act at the same time or doesn't exist at the same time. So that's why we have some load combination. So the load combination is possible under surface load condition and ultimate load condition. Most adverse combination should be used for design. The load factors for various combination are given in AS 1170.0 as follows. So the first is we have dead load alone, G alone. So the combination is 1.35 G. Second is we might have dead load plus live load, so G plus Q. So 1.2 G plus 1.5 Q. Another one is dead load stabilization and live load. So this G plus 1.5 Q. We just ignore this one now. It's not important for us here. The first one we have, or the third one we have dead load plus live load long term. So we have G plus Q long term. So it is 1.2 G plus 1.5 psi L Q. Psi L is long term factor for live load. Number 4, dead load plus live load plus wind load. So this is also important for us. So we have 1, 2, 3, 4. So dead load, live load, wind load. So we have G, Q, and wind. So we have 1.2 G plus psi C Q plus W ultimate. Psi C also is a factor for live load, and the W ultimate is the wind load. Number 5. So this is the main five combination we need to know. Dead load G plus wind load W, but wind load reversal. Wind load reversal mean wind uplift, because the wind might cause wind load, can cause like downward or uplift. So 2 cases for wind, downward and uplift or reversal. So when the wind acting upward, we take only 0.9 G plus WU. Okay, number 6 is for earthquake, which is not in our focus. So no need for this one. So these are the main 5 load combination we will be looking at in our calculation in steel. Okay, again, this is the factor: G dead load, Q live load, W wind load, psi L load factor for quasi-permanent long-term action of live load, Q, psi C imposed action for live load as well, 0.4 to 0.6. Okay, this was a load combination for strength. Let's now look at the load combination for serviceability. So for serviceability, we have fewer load combination. Similar load combination is required for serviceability, but smaller combination factor are as follows. So as you can see here, in strength, we have factors 1.35, 1.2, 1.5, all or most of them more than 1. But for serviceability, we don't have like verification factor, we have only all the factor as 1. So the first load combination for serviceability is dead load G plus live load Q, short term. So we have G plus psi SQ. Psi S means short term for live load Q. And the second is G plus psi plus live load long term. So we have G plus psi L long term. The third is dead load G plus live load Q plus wind load W. So we have G psi S, again short term, and WS. Okay, so these are the load combination for serviceability. And this table 4.1, is for the factors psi s, psi l, and psi c we found in the load combination. So for example, if we are doing a roof, so roofs like not used for floor application, like normal roof, psi s will be 0.7, psi l is 0, psi c is 0, and psi e is 0. Psi e is not our focus because we are not doing earthquake, so no need for this one. Another example, if we have a roof, floor. Again, we are focusing on the UDL only. So for roof, like office roof, so we have psi s equal to 0.7, psi l 0.4, psi c 0.4. Okay. So these are some example of the load combinations we have in the steel design. And our last step, or our last thing, is load estimation on structure members. So how to calculate the loads on structure members. Okay, so load estimation, we need to require sizes of member depending on the weight of the structure, which means load estimation and member sizing is an iterative process in which each affects the other. So to start designing the members, we need to assume the member sizes to start with. The member sizes will depend on the iterative process, so we cannot assume it from the first time. We have some shortcuts to reduce the time in trial and error process. Structure carrying heavy dead loads, concrete slabs or machinery, often dominated by dead load. Best to first size slabs or machinery to estimate the dead load. So in some structure, we have dead load dominate. In tall or high structure, lateral loads or wind load dominate. Steel framed industrial buildings in warm climates designed based on wind load. Dead load and life load normally small. Ignore for preliminary design. Estimate wind load from dimension of structure and location. Size members. Check that they can withstand the combination of dead load and wind load. Earthquakes loads are significant to structure supporting large masses. So we need to estimate the mass before sizing the structural element. So if you are designing for earthquake, for example, you need to estimate the total mass of the building before designing the member. Okay. All good. Do you have any question, guys? Okay, so now we go further to dead load estimation on columns. So for dead load calculation, and we mainly use the tributary area method or the area method. So we need to consider, for example, a slab supported directly on a grid of column. So you need to divide the slab into few grids. Each column will support the weight of the highlighted area. So this is an example of what we are using for calculating the dead loads or life loads on elements. So for example, if you have this slabs with some uniform loads on it, so if we need to calculate the load on each column, for example, this middle column or whatever, any column of them. So what we have to do is we have some dimensions in this direction, some dimension in this direction, and so on. So for example, if this dimension is 10 meter, 10 meter, here also 10 meter, 10 meter, 10 meter. So what we are doing is we have two columns here, or 2 rows of columns and 3 rows of column in this direction. So here in this direction, the distance is 10 meters. So each column will take half of the span, so half of this 10 meter. So this will be 5 meter and 5 meter. Okay, also from the other side, this column will take 5 meter and this column will take 5 meter. So this in one direction. On the other direction, this 10 meters. So each column will like divide the area between them. So we have, because this one on the edge, so it will take 5 meter. This one will take other 5 meter. This one 5 meter and so on. Okay, so if we look at the column in the middle, for example, here. So what is the supported area by this column? The supported area by this column is this blue area. Do you know what is the dimension of this area? And if you can help.
10 meters by 10 meters.
Yes, so we have 5, 5, so this side is 10 meter. And also 5 and 5, so this side is 10 meter. So this column, the tributary area of this column, equal to 10 meter by 10 meter. So how much? 100
square meters.
100 square meters. So let's say this load was 10 kVA or 10 kilonewton per square meter. So how much is the load on this column? So the load or dead load on column will be how much? The load, dead load, which is 10 kVA times what? The tributary area. Yeah, right?
1,000 kilonewtons.
Yes, so times 100 meters squared. So it will be 1,000 kilonewton. Okay. So let's say this is column C1. If I ask you quickly to help me in C2, can you help me with C2? C2 is a corner column. Is there any difference between corner column and intermediate column?
Yeah.
This is called corner column. What is the difference? All the area has same load, but what is the difference? The tributary area, right?
Yeah.
So for
it's
corner
1 by
column,
1.
yeah, the tributary area for C2 equal to how much is the dimension?
5 by 5, so
Yeah.
25 meters squared.
Yeah, 5 by 5, so 25 square meter. So the dead load on C2, for example, will be same 10 kVA times what? 25 meter square. So how much total? 250 kilonewton. Okay, so if you are asked to design the critical column of this structure, which one is critical? C1 or C2 or other column?
The one supporting 1,000.
Yeah, C1, or this is, we call it internal or intermediate column. So the internal column will carry all the time higher tributary area because it carry from all direction, like from right, left, top and bottom, right? But for corner column, it carry only from 2 sides. Okay, so this is this is what we deal with. This is called like area method, or is like approximate method, but this is usually what is used for manual calculation. Okay, let's go in an example now for dead load on support in a slab supported a single column in a 3-story. Okay, so if we have the density, we need to calculate the dead load supported by the internal column on the lower floor. So similar to what we have done, we have a slab thickness of 200 millimeter, column spacing in both direction 4, floor height is 4 meter. The weight of the column is 30 kilogram per meter. So if we look here, this direction we have 4 meter. The other direction is also 4 meter. So if we are looking at this column, the hatched area, so what is again the dimension? So this 2 meter and 2 meter. So this side is 4 meter. And what is the other side? If it is 2 meter and 2 meter, so 4 by 4. So the tributary area here, how much? 4 by 4 equal to 16 meter square. Yep, so this is the tributary area. Now how to find the load itself? Do you know how to find the load, the uniform dead load on this one? So the weight of a slab, G, equal to the thickness of a slab, 0.2, times the density of concrete. How much is the density of concrete, or gamma C? So we have T slab times gamma C, which is 5 kilonewton per cubic meter. So this kilonewton per cubic meter, that's why this should be meter. So how much the load G in kPa? 5 kilonewton per square meter. Okay, so if we need to find the weight of the column, 1-story slab, so using the tributary area, the internal column, 5 kilonewton per square meter times 16. So how much is the force? 80. For edge column, what is the edge column area? Which one is edge column? Edge column means something like this. It is on the edge, so it carry like half of the area. So how much is the dimension of this area? Do you know how much is this one? 2.
2 by
How much
4.
is the other side? 4. So how much is the tributary area for edge column? 4 by 2, which is half of the internal column, as you mentioned. So it is 8 meters. So 5 times 8, so it is 40. And the last is corner column, same load. The area of the corner column, which one is corner column? This one here. So the corner column, the area is 2 meter by 2 meter. So the area is 4 meter squared. So 5 kilonewton per square meter times 4 give us total load as 20 kilonewton. Okay, if we look here, so it was required to determine the concrete slab for a 3-story building. So how to do it for 3-story building? This load was only from 1 story. So if it is 3 stories, we need to multiply by 3. So the weight of the internal column, so the weight of the column or dead load on the column will be 3 times 80 kilonewton. But this the load only from slab. What else should be included? Do you know what else should be included for that? What is the dead loads includes? The dead loads includes the slab, which is supported by the column. So the column carries the slab. What else the column should carry or should add it to the column weight? Anyone know? Do you know the self weight? Because the column should carry itself as well, right? No, yes, beam also can be an option, but this slab doesn't have any beams. It is like flat slab. So what else should be included? The on weight of the column. So the weight, the dead load or the weight on the column will be weight from slab plus on weight. The on weight given here as this note here. Can you see this note? the weight of column is 30 kilogram per meter. So what is the total on weight for the one column? So this is our column. Let's say this is our column. Okay. The column height is given as 4 meter for each story. Okay. The weight of the column is 30 kilogram per meter. So how much is the self weight of each column?
120 kilos.
Yes, 30 kilogram per meter times 4, so it is 120 kilogram, right? So can we sum kilonewton to kilogram? So now the weight on the column will be weight from slab plus on weight. The weight from the column, sorry, the weight from slab is 3 times 80 kilonewton. The on weight of one column is 180 kilogram or 120 kilogram. So we need to convert from kilogram to kilonewton. Anyone can tell me how to convert from kilogram to kilonewton? How to convert from kilogram to kilonewton?
Multiply by gravity.
Yes, sure. So weight equal to mass times gravity, right? So G is 9.8 meter per second square. So to convert from kilogram to kilonewton, we need to multiply by 9.81, but this will convert it to Newton. So 1 Newton weight equal to 1 kilogram mass times 9.81. So how to convert Newton to kilonewton? We need to divide by
1,000.
1,000. Yes. Okay, so to convert from kilogram to kilonewton, we need to multiply by 9.81 and divide by 1,000. For simplification, we can like round this up to 10. So from kilogram to kilonewton, you need to multiply by 10 divided by 1,000. So it is like divide by
100.
100. Okay. So if the self weight is 120 kilograms, so it is equal to 1.2 kilonewton, right? Is that logic?
Yeah.
So this for one story only, right? So we calculated for one story. How many stories we have?
3.
3. So the total weight will be 1.2 times 3 as well. So we have 3 times 80 plus 3 times 1.2. This give us total 243. $243.6 kilonewton. Okay, this is the value. Is that logic? Do you have any problem with that?
No issues.
No issues. Okay, that's good. So let's jump to another example here. If you have any questions, just let me know, guys. So for this example, we have dead load of concrete slab supported on a beam. So now if we looking at another example with beam. So we need to find the dead load on a typical or internal beam and external edge beam carrying a 200 millimeter thick slab. Again, the density of concrete 25 kilonewton per cubic meter. The column is basing 4 meter, slab width 4 meter, beam length is 8 meter. The weight of the beam is for 610 UB 101 is 1 kilonewton per meter. Okay, so first of all, we don't have the weight of the slab or self weight of slab. So for the slab self weight, how much is slab self weight? The thickness is again 200, so 0.2 meter times gamma concrete is 25 kilonewton per cubic meter, so it will be 5 kilonewton per squared meter. Okay, so now how much is the load on the beam, on one beam? If we just draw what is written here, something similar to here. This is what is meant by the so if we have, this is the plan, 4 meter, 4 meter, and 4 meter, 4 meter, and so on. The important thing we need to know is the tributary area. What is the tributary area for each beam? Do you know? Anyone can help? What is the tributary area for the beams? So each beam will carry half span from each side. So this will be the tributary area. Tributary area. So the middle beam or the internal beam carry how much width of the slab? If this 2 meter, 2 meter, 2 meter, 2 meter, so how much total?
4.
4 meter. For the edge beams, how much is the width?
Only 2 meters.
2 meters, 2 meters, right? So this green area will be carried by the edge beam, which the width is 2 meter. So for the internal beam, the blue is 4 meter width. For the edge beam is 2 meter width. Okay, so for the internal beam, G internal will be 5 kilonewton, the load, times 4. What is the 4 meter means? The load width, right? What is 1 kilonewton? 1 kilonewton is the self-weight of beam. So the general rule is G for beam will be the self-weight of the beam plus the load from, or the dead load from slab, right? So self-weight of beam is equal to 1 kilonewton per meter. This is given. Plus, how much is the dead load from slab? The dead load from slab is 5 kilonewton per meter square times what? The load width. What is the load width of the beam? 4 meter. So how much is the total load on the beam, G beam? 21 kilonewton per squared meter. Is that logic?
Yep.
Yeah.
Yeah. For the external beam, what is the difference for the external beam? The only difference is the load width. The load width for the edge beam is 2 meter only, but the on width is still same, so it is 11 kilonewton. Just to have a question for you, what is the difference between column load and beam load from the two examples we had? The beam column is UDL over a length or line, right? So what is the final load unit? Because the unit is important. So what is the unit? Kilonewton per meter, right? For concentrated load, is the concentrated load, for the column, it is UDL or a point load?
Point load.
Point load. So what is the unit?
Just kilonewton.
Kilonewton. So the beam is carrying a uniform load or UDL in kilonewton per meter. For column, the column is carrying a point load B in kilonewton. Is that correct?
Yeah.
Okay, that's good. Okay, so these are some example for simple example. Just to quickly go through this one. So for roofs are often required to support dead load and wind load and live load. In industrial building, corrugated sheets is commonly used. For domestic building, we can have tiled roof or mainly tiled roof, but in the modern construction, it become steel sheet as well. Steel sheets can be used as well. Okay. And also we might have purlins and we have rafters. So we have sheeting, roof sheeting, and then we have purlins, and then we have rafters, and then we have columns. So this is the elements of like a shed, a domestic shed or a warehouse. So the purlins are supported on rafter, and the rafter, mainly steel, are heavier and more widely spaced, running at the right angle to support purlins, and the rafter are spanning between columns. So the rafter transferring the load to the column. For portal frames, the rafter are supported by column at both ends of each frame. A safe design requires loading on roof to be safely transferred through all the above mentioned structural elements, including connection. Vertical loads are transferred from roof to purlin to beams to columns to foundation to finally soil. Because this part is important to know what is or how the load transferred through the building. So can you help how the load is transferred through this building as an example? So for example, if we have, this is our roof sheeting in red, right? So the roof sheeting load will be transferred between purlins. Is that correct?
Yeah.
So in the shorter direction, the purlin will take the load from the sheeting. Then the purlins will transfer the loads in this direction to what?
The rafter.
The rafters. So the rafters will take the loads from the purlin, and this is our rafter. So we have the rafter in this direction and the other load in this direction. So after the rafter, what will happen? The rafter will transfer the load to the
The
column
column.
here. So we have column here and column at this end. And then from the column, the load will go to the footing, and then after the footing, we have the soil. So if I ask you for a load pass, the vertical load pass, the load go from the roof sheeting, then purlins, then rafters, then columns, then footings, and finally, because all the loads should go where? To the soil or the supporting soil. Okay. And here is another example. So again, if we have, this is our purlin, so the load will be transferred through the purlins like that. Then the purlins transfer the load to the rafter in these directions. Then the rafter transfers the loads in these directions to the columns. And finally, the column transferring the load to the footing. And underneath here, we might have footings, then the soil. Okay, because you need to know which member carrying which member to know what we are designing or what is the loads, where is the loads coming from. For example, if you are asked to design the rafter, what is the loads coming? Where is the loads coming from to the rafter? Do you have any idea?
Coming from the purlin.
And the rafter are carrying three things. self-weight, this is the important thing, right? And also the sheeting and the burden, right? So the rafter is carrying every element carry all the above elements. Like for example, if we are designing the column, so we need to calculate the loads on the rafter and the Berlin and the sheeting and transfer all to the column. Okay. Let's quickly look at this example here. So example on live load estimation. If we have a 0.42 custom ORB roof sheeting supported on a Berlin Z150-15 and the spacing is 1200, the rafter is 200 UB 29.8 at 5 meter centers and 10 meter in span. We need to find the live load on Berlins and rafters. Okay, so we have Berlin, sorry, this is our frame, for example. So the span is 10 meter and this is the frame. The spacing of the frames are 5 meter each. In the vertical or the longitudinal direction, we have some Berlins. These Berlins, what is the spacing of these Berlins? 1200 millimeter. So this is a small sketch of the buildings we have. So how to find the live load on this building, on this Berlin and roof sheeting, and the rafter. Let's start with the Berlin. So this is our Berlin. What we need to do to know for each Berlin or for each element, we need to know what is the tributary area. What is the tributary area for any Berlin? Each Berlin will carry half is spacing from left, half is spacing from right. So what is the width of this red area? You know?
1200 mil.
Yeah, 1200 mil, which is 1.2 meter, right? So this is the width of or load width of Berlin. So let's say we need to find the live load. For the live load, this is the formula from the Australian standard. So Q equal to 1.8 over A plus 0.12 and should be more than or equal how much? 0.25 kVA. So what we need to know, A. What is A for the Berlin? A for a Berlin, because we consider a Berlin as simply supported, so this is the area of one Berlin. What is the area of one Berlin? 5 times what? 1.2.
1.2.
So for a Berlin, A for a Berlin equal to 1.2 times 5. 5 is the span, and what is 1.2? Load width. Okay, so area of the building is 5 times 1.2. So if we substitute in the formula here, so Q will be 1.8 divided by 1.2 times 5 plus 12.12. So this gives us 0.42 kilonewton per squared meter. Is it okay or not okay? Is it more than 0.25?
Yeah, it's more.
Yeah. So if it is more than 0.25, so it is okay. Okay. So do we need to take it 1.25? Should be more than 0.25. So this is our value of the load. So the load is 0.42 kilonewton per square meter, but we need the load as line load. So how to find the load on the Berlin as line load? So Q Berlin will be equal to 0.42 times what? The load width. So what is the load width? 0.42 times 1.2 meter equal to 0.504 kilonewton per meter. Is that okay?
Yep.
Do you know how to convert from square kilonewton per square meter to meter?
Yep.
Because this is important one, so I will put it somewhere here on the left. So the idea is we have the Berlin just in 3D. The Berlin is carrying this area, right? How much is this area? The width of this area, how much? 1.2 meter. But we need to convert this yellow area to this blue line as UDL over a line. So how we concentrate this area to this line? We need to multiply the UDL times, so UDL times the load width. So the UDL was 0.42 kilonewton per square meter times load width, which is 1.2 meter. So we concentrate this yellow area to this blue line. Is that correct, or is this logic?
Yeah.
Fine.
Okay. So similarly, we will do same for the, so this is for the Berlin. So this, if this is the Berlin, the span of the Berlin, how much is the span of the Berlin? 5. How much Q on the Berlin? 0.504 kilonewton per meter. Similarly, for the rafter, what is the area supported by the rafter? If we look at the rafter here, do you know what is the tributary area for a rafter? Anyone can help? Sorry.
10 meters by
Yep, 10 meter is a span.
It's 5 because it's half and half.
Yes, by 5. Okay, so if we look here, the tributary area for the rafter is 5 by 10, because this white area, the span is 10, then the width is 5. So the tributary is 50 kilonewton. Okay, so W will be 0.25. If you go to the standard, there is a note underneath. If the area is more than 14, so the value will be less than 0.25. So what is the value you should take? 0.25. For example, if we try it, so maybe we don't know this note. So Q will be 1.8 over what? 50 plus 1.2. So this gives us a value of 0.156. Is this acceptable value to take for
No.
no, less than 0.25? So you should take it as Q equal to 0.25 kb. Is that correct? So this note is for that. If the area more than 14 meters square, this gives us directly that we need to take W as 0.25. So how much Q on the beam, on the rafter? Similar to what we have done here for the Berlin. To find Q as line load, so we need to multiply 0.25 times what? The load width. How much is the load width? 5?
5.
So how much is the final load on the beam? 1.25. Correct? So if we want to represent the rafter. So the rafter, how much is the rafter length or span? 10 meter. How much is the uniform load on the rafter? 1.25. Okay. Are you okay with that?
Yep.
Okay, I think that's enough for today. Are you happy to have a look on this example as well? Already, the time is already.
Sorry, I just have a question. I just need to leave, but just for the group assignment, I don't have a group, so I don't know how.
Okay, can take. Okay, have you started forming the group, guys, for the first assessment?
Yep, I have created a group 1 in study group, and I think we are 3 persons at the moment. Me, Pauline, and Parisa.
Okay, and the other guys, William and Nicholas and Joel.
I
Yeah.
know Elias, so I'm in a group with him, but otherwise no one else.
Yeah, I don't have a group yet.
Okay, so Baris can join with William or Nicholas. So I think we can have
Okay,
maximum
good.
of 3. Thank you, Baris, for the option, but I think 3 is enough because we already not many students, so 3 I think is enough for the group.
Okay, and how can we contact? Like,
You can join. I think on the website, the course website, there is some like this discussion board or something you can and also you can create or join a study group, or you can like contact William or Nicholas directly here if you can send them your email or something to join the group. Have you created any like study group, William or Nick?
No, I don't know how to be honest.
Yeah, I haven't either. But did you say you've got one other in your group, Nicholas?
Yeah.
Or maybe I could just shoot you an email. Maybe Paris, you could just pop an
Yeah.
email through and join the group. We can have 4, is that right, Ahmed?
3 is enough for now.
Or 3? Okay.
Yeah. So you can, Baris can join you, William, in a group because
Yeah.
Nicholas already has one. So
Yeah.
yeah. So if you can contact, like send a message here, personal or like private message between you here to take the email, or I think if you search by the name, so you can find his email. But
Yeah.
yeah. Anyway. Yeah.
Cool.
Okay. No worries. Okay, all good. Do you have any question, guys? Do you want to continue this example as well, or it's up to you? I am happy to continue for maybe 5-10 minutes if you want. If you are like, if you're already like tired or something, I can do it later or have a look on it. Yeah.
I had one quick question just about the assignment, if that's all right.
Yeah, sure, you're sure. Yeah.
Yeah. For the first question, it says it's an unbraced beam column member. I was just wondering how we know what effective length to take. Like if, you know how you showed us the table that shows you the different, like 1.2, like the different effective length factor. Do we need to consider that in the first question of the assignment?
Yes. So I just show you something here. Just a second. So this. Do you have any other question, guys? Just until I show something to
Not right now.
William?
No, all good.
Thank you. I just trying to. Yeah, sure. Can you see my screen now? So this is assessment
Yeah.
1.
Yep.
Determine the design action effect for an isolated arm-braced beam column member, which is subject to design action from a first order. The effective buckling lengths are 10 meter. This is what you mentioned, William? What you're talking about?
Yep.
Yeah, so this one is given directly because there is no like ends or support, so just the buckling length is given directly. So
Okay.
effective buckling length means LE directly given.
Okay, so there's no adjustment factor.
Yeah.
Because yep. All right. Yeah.
So
That's
it's
cool.
just simplification for the example, just directly given use a buckling LE in
Yep.
yeah.
So yeah, there's no no
Yeah.
KE effective.
Yeah.
Yeah.
Just
Okay.
so yeah, also something. Can you see this? This is a tutorial for
Yep. Yep.
week 2.
Yeah.
There's something similar, but just the values are different. So for
That's
example here, yeah, sorry.
yeah, that's a braced beam. So will that change anything? Because the other one's an unbraced.
Yeah,
beam.
but I mean, yeah, just like for braced you need to find delta B. For unbraced you need to find delta S. But I
Yep.
mean for the buckling length it's still same. You need to find this too.
Okay. Yep.
Yeah. So it doesn't change anything rather than delta. Here we find delta B, and there you need to find delta B and delta S, and delta S, yes.
Okay. Great. Thank you.
No worries. Okay. And here in this example, looking at what we have, like the K effective and so on. So can you have a look on this tutorial and let me know if you have any question?
Yeah, that's that was my
Yeah,
only
sure.
question.
Yeah, just have a look and maybe I can record a short video like explaining this like one of the example along like in details, in depth.
So can we see tutorials on the
Yes.
tutorial
Yeah, the
content
tutorial and
and the
tutorial
answer?
answer are there, so I'll just show you.
Thank you.
You haven't accessed the first one, the first week tutorial? I
Sorry.
think we already tried the tutorial question last week, and you have access to it, right? Or yeah, can you see my screen now?
Yeah.
Yeah. So under week 2 tutorial, content, here is
Yeah.
a tutorial 2, tutorial question, and tutorial question with answers.
Yeah. Thank you.
No worries. Just if you can have a look, guys, on the tutorial question and answer, and let me know if you have any problems, so we can like record a video explaining one of the or the ones that have difficulties for you. Is that okay?
Yeah, that sounds good.
No worries. So you guys, each session we have one tutorial question, right? No, this tutorial question for, yeah, you mean one file or one tutorial question? Yeah, we have each session we have one tutorial file. Okay. I'll just maybe return back to if you have like more 5 minutes. Can we have more 5 minutes?
Yeah, that's fine.
Okay, thank you. Just trying to. There is a share. Can you see the screen? Can you see anything from my screen?
It's just
Yeah,
on
we
the
can.
tutorial.
Okay, just the Zoom app doesn't respond, so just wait for a few seconds.
Just another question, Ahmed, about the group. If there's already a group of 3 and a group of 2, should Paris and I just form a group of 2, or will we need to someone have a group of
So
4?
I don't know how many students are engaged in the course now. So is there any other members you know that they form a group already or not? If not, you can join Nicholas group. So the other option is you and Paris will join Nicholas group. But I don't know if there is any other members that willing to join or have already formed any group.
Okay.
If you can check, so it's okay. I'm happy to make 4, but 4 maximum. So
Yeah.
if you want to make 4, if 4 would be like easier for you, I'm happy to.
Okay, sure. I might just grab your email, Nicholas, before you go, if that's cool.
Yeah, that's fine.
It seems that will not respond. I need to close the Zoom session too. Okay, anyway, guys, so I think the time I will maybe record this part, like going through the one of the example, the last example in the session, and send it to you as well. Okay, is that fine? Because the Zoom application is like crashed as well, and I need to close the program, so don't need to waste your time again. So
Yes, thank you.
I will do it, and just if you can also go through the tutorials and try the example and let me know, so I can add it to the recording as well if you want.
If we have issues, are we able to email you?
Yeah, sure. Do you have my email? Or
Yeah, from the file you sent last week.
yeah. Just send to this email anytime.
Okay, thank you.
No worries, guys. Okay, guys, thank you for attending today, and see you next week.
Thank you so much.
And thank you, Bars. We will meet on Monday, so this just an exceptional week. Are you okay?
Yeah, that's
Monday's
great.
Yeah, okay, thank you.
Yeah.
Just
Yeah,
make sure
that's
that
fine.
you are on same page. Okay, thank you, guys.
Yeah, thank you.
See you.
Thank you.
Thank you.
Bye.
See you. Bye.
See you then.
Bye. See you. Bye.